Okay, we are now in chapter 11. And 1 minute. We are now in chapter 11. And in this chapter, we are talking about something new. Now, of course, it's about inference about a mean, but when we have small samples, remember in the previous chapters, we always had sample size to be at least 25. Okay, so how do we deal with a situation when you have less than 25? Okay, all right. So in such situations, we need to work with a different distribution called student t distribution. So we won't be working with the z distribution or the standard normal distribution, the bell curve with mean 0 and standard deviation 1. We will be working with the student t distribution. Okay, so this is something new that we are going to learn. Okay, actually there are lots of things which are similar to what we have been talking about in chapter 9, when we dealt with I'm sorry, chapter 11, chapter 10, confidence intervals. The main difference is that instead of using the standard normal distribution, which is the z curve, we will be using the student t. Okay, that's pretty much what the major difference is. Okay, all right, so let's get started. um, so now, okay, so we are going to talk about in this chapter would be um, estimated standard error of the mean. Remember SE. So we are going to make a modification in this chapter when we deal with small samples. Then we are going to learn about students t distribution. Okay, the one sample t test. Okay, confidence interval for the mean mu. Then paired samples. Now this is something new, very important and useful, especially in biostatistics. We will be using that. And then conditions for inference. Okay, now sample size and power, I would be sort of we'll do some problems with sample size, but power we will not be doing. For I will have the slides here, but I will not hold you responsible, for as far as exam is concerned, with the topic power. Okay, now that's a little bit advanced. If you are interested, certainly you can read, and we can discuss, but you don't have to worry about power as far as the exams and the problem sets go. Okay, but definitely that's an important topic later on when if you were to do more advanced stat courses. And also if you have to do actual stat projects, power is an important thing to know about. Okay, all right, so let's go to the next slide. Okay, so estimated standard error of the mean. Now remember, standard error formula was sigma over square root n. Okay. Now, of course, you may have guessed, you know, sigma is a population parameter, so we do not know it. That's what I have been telling you all the time. Population parameters are not known, so we actually very rarely know the actual value for sample standard population standard deviation, which is sigma, but that comes in that formula, remember. So since we do not know, we estimate it by the sample standard deviation. Okay, now this estimation of replacing um, sigma by s is pretty good if you have large samples. But see, there are lots of times that we deal with small samples, especially in biostatistics, because we deal with humans. Getting data from humans is not easy. It's not like for Wall Street or something where you have lots of data coming almost every day. Okay, so we have to pay a lot of attention on small samples in biostatistics. Okay, so if you do not have a large enough sample, this estimation is not good. Um, we will have this formula s over square root n, but we can no more think of s as a constant sigma value. Okay, if this sample size is not large enough. then what happens is this S varies from one sample to the other, right? So there is some source of uncertainty coming for this standard error of X bar because of S. Okay, because the N is of course constant. Because of S, standard error keeps on changing. So when standard error keeps on changing, we cannot use the Z procedure anymore. Z procedure meaning we cannot use the Z scores. Okay, for the z-scores, you need to have the denominator to be constant. Remember, sigma over square root n. So then, when you have this as, we need to work with a new procedure, which we call to be T procedure. That means why we call it a T procedure is we will work with a T statistic instead of a Z statistic. Now, Z statistic, Z score, they are pretty much the same. Z score is the more commonly used word, but actually Z statistic is exactly the same. Now, instead of the Z statistic, we will have to use the T statistic if you have a small sample. Okay. Now, T statistic we will realize is pretty much almost the same as the Z statistic. Okay, that's the nice thing about this chapter. We have learned more than 75%. That we need for here. Only a little bit new things we will be learning in this chapter. Okay, but it is good. It is good review actually. All right. Okay, so now here let's talk about the student t distribution. Now this is also a probability distribution. Okay, it is it is a family of distribution. It is not like the standard normal curve, which is exactly one. Standard normal curve means it's a bell curve with mean 0, standard deviation 1. Now student t distribution has some kind of a parameter or a variable, if you want to call it, which is called the degrees of freedom. Now, if you consider only one sample, as we do in this chapter, now later on we will be considering two samples as well, where we have to compare the means between two different populations, like males versus females and so forth. But here in this chapter, we are dealing only with one sample. And in fact, even in previous chapters, we have been dealing so far with only one sample, only one mu, right? Then the degrees of freedom will be n minus 1. Okay, so if you have 25, degrees of freedom will be 24. Now you will have the t distribution to be symmetric. Okay, t distributions are similar to z. The mean will be 0. Okay, mean will be 0 and it is symmetric. Now the difference is based on this df, it will have the shape to be slightly different. But as you increase n, so that df will increase, the t distribution gets very much like the z distribution. Okay, now remember, z distribution is a standard normal distribution. Oops, I have to correct this. And that means the mean is 0 and standard deviation 1. Okay, so let's go to the next slide. So here's like a picture which gives you an idea of how to compare the student t distributions with the standard normal. Okay, let's see. Yeah, okay. Now, if you have degrees of freedom to be 1, this is the curve, then degrees of freedom to be 9, then degrees of freedom to be infinity. Infinity is really large. Then it is a Z curve. See, do you see that Z? So what this picture is telling is, as you increase the degrees of freedom, this curve gets closer and closer to the Z curve, which is a standard normal curve, which has a mean 0, standard deviation 1. Okay, so in other words, if you have the sample size to be really large, t and the z are pretty much the same. So that's what happens when you have sample size to be large. You don't have to use t anymore. You can go back to your z. Okay, actually for practical purposes, infinity is around 25. Okay, for practical purposes. All right, so if you have about 25 samples, you don't have to work with the t distribution. You can work with the bell curve, which is a standard normal. Okay, all right. So let's go to the next slide. Okay, so now t distribution, the t values are actually tabled or tabulated. Okay, now in your book it's on page 545, table C. Also you can get it from lots of software. Excel has it, Minitab has it, lots of other software has it. Okay, now usually you will have t values in the table as the entries, like just like the z tables. Of course, on the left side you will have the degrees of freedom, and the columns are separated based on the probabilities. So let's see how that looks in the next slide. So here's like a portion of the table, the student t distribution. Now see, degrees of freedom you will see in the big table, you will have degrees of freedom 9, degrees of freedom 10, and so forth. All these rows, coming down this way. And then on top you will have the cumulative p. Cumulative p means the percentile. Okay, so it's like the left side up to this point. Now upper tail p means this value. Okay, so like for example, if you have cumulative to be 0.75, that means this entire part is 0.75. Then the upper tail will be 1 minus 0.75, which will give you 0.25. So you can see that this and this should add to 1, right? So cumulative plus the upper tail will be 1, because cumulative means, as I have mentioned in here, cumulative p. For example, now see in here I have sort of explained here for 0.9, it is left tail plus the middle. So if you have a 0.9, left tail will be 0.1 and the middle will be 0.8. So you will have 0.9 to be the cumulative p. Okay, and the upper tail will be also 0.1. So this and this are the same. Okay, all right. So the table will have entries. Now these are the entries. So you will have a whole lot of entries as you keep on having different degrees of freedom. These entries are the t values. Just like the way you got the z statistic value, you will get the t value. Okay, so for the t value, you can find the corresponding cumulative p. Of course, if you find this, you can get the upper tail. Okay, so for example, if you are working with degrees of freedom equal to 9, so if you have one sample, what is the sample size? 10, correct? Because degrees of freedom will be in minus 1. So for degrees of freedom to be 9, n has to be 10, right? So with degrees of freedom to be 9, if you get a t statistic, once you calculate it, t value to be 1.383, then the cumulative, see right here is 1.383. The cumulative is the entire left portion will be 0.9, okay, and the upper tail will be 0.1. Now actually, let's go back to p-value that we discussed in chapter 9. How do you get the p-value? P-value is what is to the right of the test statistic, right? So if you have a t-value of 1.383, the p will be 0.1. So that's what I have mentioned in here. Okay, I need to put note here. Oops. Okay, so remember, whenever you have a p-value, whenever you have a test statistic, now in this case it's a t-value, the p-value is the the probability to the right. Okay, all right. And then also remember, to get a two-sided p-value, you need to double that. Okay, so we will be sort of becoming more and more familiar with this stuff as we do problems. Okay, but as I go along, I will be sort of bringing everything that we have, almost everything that I can remember we studied before in chapter 9 and 10 again and again, so that we will all be more familiar with things, because there's so much that we are learning in a short period of time, right? Okay, so let's go to the next slide. So here's what they have shown in a larger picture. So you have if you have 1.383, the upper tail was 0.1. Actually, this is the p-value corresponding to a t of 1.383. And then of course this is you can again say that 90th percentile means this portion is 0.9, 90th percentile. If you have a degree of freedom to be 9, is 1.383. Now, by the way, when you write like this is actually degrees of freedom. Okay, this is the degrees of freedom. In fact, I should go back and explain that to you. Right here, see, they have T 9, comma 0.9. So this 9 stands for degrees of freedom, and zero point 0.9 is the left probability or the cumulative probability. Okay, so that is sort of notation. 9 is the degrees of freedom, zero point 0.9 is the cumulative probability. Okay, all right, let's go here. Now, okay, so one sample t-test. Now this we will do when n is 1. So if you sort of compare with chapter 9, the hypothesis that we set up is exactly the same. We will always have the null hypothesis to be mean equal to a specific mean mu 0. You can have a two-sided test where we say mean is not equal to that specific value, or you can have a left-sided test, which means mean is less than that specific value, or you can have mean to be more than that specific value. So now remember, the null hypothesis always has equals. The alternative hypothesis will have either not equal or less than or greater. It will have only one of these three. Okay, all right, so there are three possibilities for the alternative. Now once you have that, remember you so the test statistic, when you have small samples, we will call it T x bar minus mu sub 0 divided by s over square root n. Isn't this familiar? The only difference is you have s instead of sigma. Okay. Now also remember, when you talk about a t, you need to know what the degrees of freedom is. Otherwise you cannot figure out the p-value, right? So you need to always write the degrees of freedom, whenever you're working with a t statistic. Okay. Now once you have the t statistic, you can calculate the p-value by converting the t, which is on the x-axis or the horizontal axis. So the p-value is the probability of the curve to the right. Okay. Now you can get it from the table approximately, not exactly, because for the t statistics, the values are not given for every cumulative p. See, if I go back right here, let me go back to that slide. See, look, they give you for cumulative 0.75, 0.80, 0.85. What about like 0.77? You don't have it. So in other words, the t values are not there for every value on the x-axis. Okay, and then p values are not there for every possible proportion. Okay, so approximately you can find the p value. So let me go back to that our current slide. Let's see, where is it? Yeah. So you can find it approximately if you are to use tables, but if you have software, you can get the exact value. Okay, like Minitab, Excel will give you the exact values. Okay, so you will convert the t to the p, and then if you have a small p, that means, remember, that means small p means you reject H null. That means you are accepting HA. Okay, so that's how it is. And then, now see, remember the traditional way of making a decision. You will have the significance level, which is like alpha to be 0.05 or 0.01. And then what you do is you look to see whether p is smaller than that value or not. If p is smaller than that value, you will reject H null and accept HA. Okay, so small p means HA is favored. Alternative hypothesis is favored if p is small. Okay, all right. So let's go to the next one. Okay, so now this is just an example of how you do a t-test for the one sample. So do SIDS babies have lower than average birth weights? Now we know from prior research that mean birth weight of the non-SID babies is 33,000 grams in the population. So we will study only 10 SIDS babies because SIDS babies are not that common. So because of that, you cannot have a large sample. So in situations like this, we have to resort to the T statistic, right? So now we will determine the mean based on these 10 babies. And then we get this value, the sample mean to be this much with a standard deviation. Now this is a sample standard deviation 720. So now the question is, now does this data, does the data from this sample tell us go with this claim or not? Okay, now we have, of course, the point estimate. Now this is the point estimate for the mean birth weight for SIDS babies, the actual birth weight. Now is that actual birth weight, which we do not know, that is mu for SIDS babies. Is the mu for SIDS babies smaller than 3300? That's the idea, or that is the claim, or that is our hypothesis, or that is our research question. Okay, but this is the sample mean. Based on these 10 babies, we know it is 2890, but this is just a sample mean. If you take another sample, it could be something else. So just by looking at this, you cannot come to a decision. You have to do a statistical test. Okay, so now let's see how we do that in the next slide. So we set up so these are the steps. Remember, when you do a hypothesis test, you set up your null hypothesis, alternative hypothesis. Okay, so now here they have put the mean to be 3300. Now see, actually if you go back in here, okay, do the babies have lower? Now actually speaking, this should have been not equal to. I'm sorry, this should have been less than according to that. Now, see, these slides I got from the book, so I'm just sticking to that. So now this means we are testing whether the SIDS babies, the average actual birth weight of SIDS babies is not equal to 3300. Okay, so this is a two-sided test. So now the T statistic is X bar is 2890.5 minus mu sub 0 is 3300. Then you got the S to be 720 in the previous slide, N was 10. So if you work it out, you get a negative 1.8. Okay, so it's a negative. Now degrees of freedom is important, N minus 1, which is 9. So if you look at the tables, you can approximately get the p-value. Now let's see how we how we get the approximate p-value using tables, which is described in the next slide. Now if you sort of compare this with a traditional alpha 0.1, now this p-value is slightly larger than that. So which means this is not right. If p is point, this is yeah, okay, I think yeah, p.105 is correct. I just checked something. Okay, so now, okay, so the p that you got is 0.10, and then the alpha, if you set your significance level to be 0.10, now this is only slightly larger than this. So you can tell that, okay, this is sort of like on the borderline at this alpha. So there is like weak evidence against H0. Actually speaking, you could even say that you could even say that weak evidence for H null also, because this is a little bit larger than this. Okay, so this is like a gray area. This value is a gray value sort of, if you have the alpha to be 0.1. Okay, all right, let's go to the next one. Now in the next slide, this next slide shows how you get the p-value to be 0.10 for a t statistic of negative 1.8. Okay, now it doesn't matter whether the t is negative or positive. to get the p-value, we will just ignore the minus. Okay, so let's go to the next slide. Okay, so what you do is to get the t-statistic, to get the p-value, if you have the t-statistic using a table. Now see, they give the 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 p-values or the probabilities only for certain values, right? And then so degrees of freedom 9. Now our t-statistic worked out to be negative 1.8, but we are going to ignore negative, so that is why they have this absolute value. Absolute value means you remove the you ignore the negative sign. So your absolute t-stat is 1.8. Now we will look in the table, whereabout is 1.8 occurring. So it's between 1.38 and 1.8. Now see, you need to look in the correct degrees of freedom. Okay, we have degrees of freedom to be 9. So which means if you look if you look the 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 left probability for 1.8 will be, it will be less than 0.9 but not as much as 0.95. So that means, okay, and then the tail probability will be something in between zero point 0.1 and 0.05. Okay, so you need to make a you need to make an approximation and then figure out what it is. Now that is if you are to look up the tables, or you can use software and straight away figure out, and then the software will give that p is 0.1054. Okay, um now that is, of course, now wait a minute. Now this is for two tails. If you do the software, you will get the two tails to be 0.1054. Now remember, the two tails p is equal to twice the one tailed p, right? So if you divide 1054 by 2, then you will get something like, let me do the working here. So you will get a one tailed p equals 0.1054 divided by 2, which is about 0.05 0527, right? About okay. Yeah, okay, so now that is, now if you do using the software. Now see, if you have the table, you sort of have to see, okay, it's somewhere between 0.1 and 0.05. Now 1.8 is much closer to this, so maybe you can approximately say it's about 0.06 or something like that. That's fine. Okay, now software of course gives a more accurate value. All right, so if you did not have software using a table, I would have said, okay, 1.8 is much closer to 1.8 than 1.38, and then I will get this value to be like 0.06. The one tail p value. Okay, see, it's only the upper tail. One tail p value will be 0.06, and then the two tail will be twice as much. Okay, so which will be 0.12. Okay, but the exact value that you get from the software will be 0.1054. Okay, so they have in fact divided the 0.1054 into each tail, and then each of them will have 0.0527. Okay, so in other words, the p-value for a one-tail test will be 0.05. P-value for a two-tail test is 0.1054. Okay. Okay, so now just to go back, now see, because this p-value is pretty, like, it is not really small. So what can we conclude? We can conclude that probably the SIDS baby's average weight is not that different from the regular babies in the population. Okay, because p is not small. All right. Now that, or even if you want to think, are their weights really low? That means it is like a one tail test, which is a left tail test. even that one now, see the p-value is 0.05. So p-value 0.05 is also not that small enough to reject the null hypothesis. So you really cannot say that, on the average, six babies weights, average weight is that less than the regular um, weight of the weight of regular babies. Okay, so let's go to the next slide. Now in here, yeah, I think I will stop here, and then because see, when the presentation gets big, it's hard for me um, to download. So let me finish here. So, and then I will continue in the next presentation, the remaining slides. Okay.